I'm trying to minimize this window here. There we go. Okay. All right, cool. Hi, everyone. Thank you so much for being here. My name is Bernadette. I'm a PhD candidate in the Planetary Chemical Analysis and Astrobiology Lab at Tufts University. And today I'll be talking about some of our preliminary findings regarding chlorine dioxide gas generation and its effects on potential Martian biomarkers in the grand scheme of the search for life. But before I get into that, I'd just like to share a bit about how I came to do this work. This one, click forward. I think it's really important when talking about science, particularly as a young person, to show alternative pathways to achieving a dream and reaching high levels of scientific discovery. I think many of us, at least in my generation and those before me, have at some point said, I want to work for NASA. And I was no exception. I came from a working class family where there were times I attended school while unhoused. And working for NASA just kind of seemed like a big enough dream to hold on to during particularly difficult times. So I'm a first generation college student. A lot of my academic pursuit has kind of felt like blindly feeling around in the dark. But even if I barely knew what steps I was supposed to take to get to this nebulous idea of success that I dreamt of, I was able to watch other people around me and learn. Next, sorry. So I graduated from a small liberal arts college in the Berkshires where I studied chemistry and biochemistry. I had no financial contribution from my family, but I was able to attend with some great scholarships and grants I applied for, as well as working nights in a local emergency department. A lot happened while I was in undergrad, multiple family deaths, including my older brother, and I had to take a leave of absence from school to fund and organize funerals. But when I returned to school, I had a really great faculty support system due to it being a smaller school. And I managed to not just get by, but excel in that program. I also met my now husband, who you can see in this photo, in undergrad. He was a math student. We actually ended up solving the two body problem, and we're both accepted to Tufts at the same time together. So that was really neat. But before that, in between undergrad and graduate school, I worked for 3 years as a chemistry lab technician and hazardous waste manager. I wasn't really sure what I wanted to do post undergrad yet, but I knew I wanted to utilize my degree in some way. And I really loved this job. I miss this job still. And I think that my experiences here, preparing labs, running instruments, and developing really an independent skill set led me to be a competitive candidate for graduate school, even though I had done no research while an undergrad student, because that wasn't accessible to me. So here I am at graduate school. I only wanted to come to Tufts, so I didn't really have a safety net, as some folks say you should shoot for. I came here to do the work I dreamt of as a kid in a chemistry lab funded by NASA. So currently, I'm working on understanding the Martian surface. We're going to talk about that today, and developing ion selective electrodes to send to the ocean moon Enceladus, all within the search for life. But it also hasn't been a smooth ride at graduate school. So while here at Tufts, my mother was diagnosed with terminal leukemia and passed away. I had to get approved for an IEP due to prolonged grief disorder. In graduate school, I had never had an IEP before, and just this past year, I was diagnosed with a chronic painful disease and required major surgery. All of this while trying to perform research and teaching. And I say this in a bit of a non-traditional disclosure, but in a way, my career itself has been a little non-traditional. I wanted to tell a little bit of my story because sometimes pursuing which has not been pursued before can get tiring. You may not see yourself reflected in those already at the table, and life can get in the way not just once, but over and over. But that doesn't mean your path is not meant for you. Adversity does not need to foreshadow an end. Life might challenge you in ways that, you haven't experienced in or out of the lab. But if there is one thing that we living beings are exceedingly good at, it is finding a way. Life finds a way. But how? And what does life that survives vicissitude or obstacle really even look like? So the Earth seems so big because we're on it, but by any other metric, we are infinitesimally small. This is a very famous photo called the pale blue dot. It was taken by Voyager 1 some 3.7 billion miles from the sun. And this is us. We are on that dot. Every single person you have ever known has lived on this dot, and wondering whether or not we're alone on that dot is a fundamental question of humankind. So, why search for life? Well, we still have a lot of things that we don't know about ourselves as a planet. So, while finding life somewhere else would be unquestionably cool at face value, the search for life beyond Earth is about more than simply finding it. At the heart of this scientific endeavor is a form of existentialism. Why are we here? Are we alone? And in a bid to answer those questions, we are looking for our own reflection. We are searching for a past and a future. We don't know how life begins and survives. Is life rare? Is it easy to start? How does it start? And perhaps most dauntingly, when thinking about a reflection, how long does it last? As a reminder, in the search for life beyond Earth, we can really only look for life as we know it. So we search in places that have either a history of similarities with Earth or current similarities with Earth. Mars, our next closest neighbor in the search for life beyond Earth, has large promise for finding it. There are marked similarities between our planet and the red one next door. Around 3.5 billion years ago, Mars was a lot closer to what Earth is today. Think liquid oceans, a magnetic field, a thicker atmosphere. And additionally, mission data shows that Mars has all the chemical nutrients that life as we know it needs. So, given the similarities between the two planets, we're drawn to the question, could the steps that led to life on Earth have also happened on Mars? So, there are several things we take into account when searching for life beyond Earth. And here I've divided them into three categories: where we are looking, how we are looking, and what we are looking for. So, the environment aspect is pretty simple. We are looking for life on Mars. The instruments are a little bit harder. We can only use instruments or instrumentation that currently exists. We are limited by what we are currently able to do right now. And then the difficulty around the biomarkers or the biomolecules of the life that we're looking for is tied to the instrumentation. So the difficulty, we can only analyze what we already know exists. So how do we detect something that we've never seen before? The way that we do this in our lab is by throwing everything environmentally that we can at a few select life essential molecules and seeing what they turn into. Whatever they turn into can guide what we search for with the instrumentation that we currently have up there. So we know that we want to search for life or evidence of life on Mars. And we also know, due to a wealth of prior discovery and research, that Mars holds both a history and modern presence of environmental factors that can impact the stability of life as we know it. So variables like impact events, solar energy particles, galactic cosmic rays, chemical oxidants, and UV radiation can all individually and cumulatively alter the existence of life. And today, in my work, I focus on the UV radiation of chemical oxidants on the surface of Mars. And we're really thinking about this big question, how do those processes affect life? So in 2009, the Phoenix lander detected about zero point 0.5 to zero point 0.6 weight percent perchlorate in the Martian soil. And since then, various levels of perchlorate have been found all over the surface of Mars. So essentially, Mars is a planet covered in bleach. We also know from prior research that there are several proposed methods of perchlorate formation on Mars, such as electrostatic discharge, ozone interactions, and the UV-driven salt mineral reactions I'll talk about today. So there are numerous ways established for how perchlorate, as well as other oxychlorine species, can form on Mars. So, prior work in our lab published in Nature in 2024 has shown that the UV irradiation of sodium chloride, which we see here, the ClO2, will generate chlorine dioxide gas, which can permeate below its point of generation in its gas phase. So, chlorine dioxide, I'll just click forward. There we go. Chlorine dioxide is known to disrupt cell membranes and oxidize critical cell components. So, it's a pretty abrasive molecule in regard to the preservation of life. So while there's been some speculation that the shallow subsurface of Mars is an ideal location for the persistence of life, it is possible that if there was or is life there, it is interacting with chlorine dioxide gas. Sorry, my mouse won't click forward. There we go. So we also know that the generation of this gas can affect simple organic structures, such as alanine, which you see pictured here. It was observed in 2024 that an increase relative humidity and thus an increase in the formation of this gas, chlorine dioxide, resulted in a lower recovery of alanine. And we can see this here on the left-hand side in row 2, where there was a 2% total recovery within a 25% relative humidity environment. So at that 25% relative humidity, we're generating this chlorine dioxide gas. That gas is interacting with the alanine, and we're not getting a lot of alanine in our recovery. Additionally, lower temperatures seem to favor the production of less oxidized oxychlorine. So here on the right-hand side, we see this as the temperature is dropped from 22 centigrade to negative 15. Chloride and chlorate, or Cl minus and ClO2, dominate over chlorate and perchlorate, ClO3 and ClO4. So what does that mean in regard to Mars? Well, Mars is a surface that is quite cold, so it's likely that the production of chlorine dioxide gas is more favored than its counterparts in that environment. So, how then do we recognize life in that environment? How do we detect life as we know it in an environment that can change life as we know it or degrade life as we know it? Perhaps in this environment, life is surviving as we don't know it, meaning it is taking shape differently in the Martian environment than it would on Earth. One way of improving our odds of life detection or recognition lies in exploring said life or biological molecules in a simulated Martian environment in lab. So this leads me to the main questions of my research. How does chlorine dioxide gas affect complex biological structures, or how can the complexity of a structure maybe offer some resistance to degradation against this gas? And then how much chlorine dioxide gas are we actually generating in a Martian environment? How can we quantify it? So this work is split into two paths. One of them is understanding the gas itself and how to measure it. And then the other is understanding how that gas affects biological molecules, which I will often refer to throughout this presentation as biomarkers. And I think that the most straightforward way to talk about this work is by starting with the gas generation and then moving on to how it affects the molecules we're interested in. So to do this, we use a Mars simulation chamber, which you can see a diagram of here. This chamber is equipped to recreate a variety of habitability factors, including pressures, atmospheric mixtures, controlled temperatures, relative humidity, as well as, of course, the Mars solar intensity spectrum. So that's between 190 to 400 nanometers of light for this UV lamp. We can also attach different instruments to our chambers via port, such as a real gas analyzer or electrochemical sensors. So inside the chamber, we run our experiments. We use a layered glass filter paper approach where our regolith simulant sits on top of the filter paper directly beneath the UV light, which you can see in this figure here. And then within the chamber, we also have a small beaker of ice water, and we rely upon its vapor pressure to provide relative humidity. We don't have a humidified gas line. And if you're wondering why, I'll save you the question later. It's because it's really expensive. But using the vapor pressure of ice water works really well, and we've gotten consistent results. So the humidity levels that I utilize are all pretty small. They're all below 30%. So technically, all of this could be considered arid. But for our work, we're going to define arid as sub 10% relative humidity when compared to our 20 and 30% experiments. So when we turn on our UV lamp, which shines through this little circle, which is a window on the top of this figure, our timer begins. We run really short time scales, less than 20 minutes right now for these experiments. And in that short time, we are generating chlorine dioxide gas. To analyze the environmental results of these experiments, we use three methods. We use mass loss of the starting regolith simulant. So we weigh it before and after the experiment. We use an electrochemical gas sensor to measure the gas within the atmosphere of the chamber directly. And then we also use ion chromatographic analysis of the ice water when it is present in the chamber. So we use a variety of surface simulants in this work. Some of them are isolated minerals like silica, and some of them are mixtures, such as the MMS1 simulant, which includes silicates as well as a bunch of metal oxides that we see on Mars. So here we see halite or sodium chloride, as well as three oxychlorine species in MMS1 mixtures. And each of these is separately evaluated with identical parameters. So each one of these constitute an experiment in and of itself where we generate the gas and see what happens. So our mass loss analysis shows a very small total mass loss. But if we assume that the oxychlorine species is the only thing readily sublimating when talking about rocks also present, we see an average loss of around 5% across all four species in simulant in a 20% relative humidity environment. So as for where that mass may be going, in these short UV irradiated experiments, we know at least one gas is forming, which I'll talk about next. However, it is likely other species of gas forming as well, given intermediates previously predicted in literature. So this indicates that all four salt species, or oxychlorine and halite species, within a Mars simulant are forming chlorine dioxide gas or a chlorine-containing gas of some kind. So we detect chlorine dioxide with our electrochemical sensor, which is built into the V1 port you see over here in this left figure. Currently, we run the experiment within the vacuum chamber and then release pressure via the G1 port to flow gas toward the sensor. While this sensor can survive the 7 millibar pressure that we run, which I only know because I tested it, wasn't on the website. Regular exposure to low pressures can decrease the capacitance of circuits over time. So that can destroy the sensor. So that's why we elected to run it outside of the chamber and flood gas toward it instead of having it inside the chamber itself. So this model is a Honeywell model, and it detects chlorine dioxide between 0 and 1 ppm with a resolution of 0.01 ppm, which is a really great resolution for this work. And depending on the relative humidity of the experiments, we demonstrate the formation of this gas between 0.2 and 0.8 ppm of this gas. This is within the values we've selected for these experiments. We have run where we have increased the amount of oxychlorine that we start with, and that produces quite a bit more gas. But the problem with that is it breaks the sensor. So that's why we have to keep our values low. We also want to keep them low because they're low on the surface of Mars as well. So if we're trying to mimic the Martian surface, we want to be as close as we possibly can. But this sensor, I will mention, it It will detect other gas. It is overwhelmingly selective for chlorine dioxide, but it will also respond to chlorine by itself. But regardless, the amount of gas that we appear to be forming likely does not account for all of what we are losing. So therefore, we needed to determine where else we might be losing mass. So one place that we could be losing mass is with gas dissolution. As I mentioned previously, we also analyze the ice samples in our chamber. As the ice samples are within the same small volume chamber that the gas is forming, it is likely that the gas will interact with and discretely dissolve within that ice melt. And I say discretely, meaning without dissociating into its component parts, because that is typically what chlorine dioxide does. The ClO2 gas will dissolve within water to ClO2 minus, the anion of chloride. So to analyze these samples, we use ion chromatography. And the concept of ion chromatography is it follows other chromatographic methods where the analyte is passed through a stationary phase where it can interact with and elute at different retention times before reaching a detector. So here we are using a liquid medium and we use an electrical conductivity detector. So that means the peaks you see here in these figures, they correspond to changes in conductivity as the ion passes through. And then they represent the different ions that we see in the ice, which you can see labeled on screen here. We use two separate columns to detect varying levels of all four species, amongst others, in these samples. And that's because some of the columns are a little bit more selective for specific oxychlorines, like here on the right. The AS16 column is really, really good at resolving perchlorate, whereas the AS18 column is not as good at perchlorate, but it's much better at resolving the other oxychlorine species. Very commonly used in water analysis. So this is a great technique for this work. So we do observe some trends in this analysis. So all four experimental ice samples have chloride above the levels of the blanks with fairly consistent concentrations to begin with. We also observe that there is a significant chlorate presence, particularly in the chlorite simulant sample, which you can see here in column 2, the 5% ClO2 and MMS1. We know that chlorite in the MMS1 produces the chlorine dioxide gas. However, it's possible, as I've mentioned, that other gases such as HCl gas or just chlorine gas by itself are forming. These different gas species could account for the varying levels of ions that we observe in the local ice, such as the presence of chloride in all four sample types, when we originally believed that the chlorine dioxide gas would dissolve discretely, meaning it would be ClO2 only in the water, not Cl minus. But what is perhaps the most interesting result from this analysis is the presence of perchlorate in that ClO2 experimental ice sample set. There is precedent for the photodimerization of chlorine dioxide gas under UV light, and that forms a compound called chlorine perchlorate. And so that's Cl2O4. So as chlorine perchlorate, it's an asymmetric oxide, meaning one of the oxygens coming off that primary chlorine is attached to another chlorine. So it's possible that the reaction with water removes a chlorine from the molecule to create dissolved perchlorate. However, because of the large amount of chlorate present in this sample, it can also be theorized that the production of chlorate can drive the reaction toward the formation of perchlorate in the presence of the mineral mixture, which does agree with prior literature published by Carrier and Cunaves. So it's difficult to truly quantify the changes in oxychlorines here, particularly chlorine dioxide, due to its reactivity, especially because our chambers are not equipped with Raman or near-infrared capabilities. All three of the proposed gases that I've mentioned have relatively short half-lives. And then they're additionally susceptible to photodecomposition in both atmospheres and aqueous solutions, which is, as you may have noticed, the two things that I'm concerned about. So not only are we generating gases quickly in this simulated Martian environment, but we're also likely losing them just as quickly to adsorption on minerals, dissolution in ice and brine, and then photodecomposition in both of those environments. So let's summarize what we've talked about here in regard to the gas generation before moving on to the biomarkers. So the UV radiation of oxychlorine MMS1 mixtures in a Martian environment will produce various chlorine-containing gases, likely chlorine dioxide, which we have detected, and possibly HCl and Cl2. One of the ways we could probably differentiate between those is by using a real gas analyzer, but that would require us to increase the concentrations of our starting material, which could damage the chamber. These gases, specifically the chlorine dioxide, readily dissolve in ice water at low pressures in a CO2 dominant atmosphere, which is what we see on Mars, typically without dissociation. However, as we've seen here, this can change with irradiation. The oxychlorine species change within the atmosphere, regolith, and brine in an irradiated environment. This can change how we interpret results from Mars. And then the pathways of formation that we are seeing appear to include that an abundance of chlorate could precede the presence of perchlorate on the Martian surface. So now we've talked about the fact that the gas is generating. It can kind of permeate all around the local environment into brine. It can go below the surface. And now we're going to get into how that gas then can affect biological compounds. So, what biomarkers are we looking at? So, I'm particularly interested in porphyrins, not just because they are looking really cool and they're pretty colors, but also because of their importance to life. So, we know that porphyrins are necessary for aerobic respiration, like in our blood. And additionally, porphyrins are found in chlorophyll, right? It's a functional component of plant life that serves purpose in photosynthesis, how they survive. So, because porphyrin belongs to two metabolic processes across taxa, it's theorized that this compound or molecules that contain this compound originated early on in evolutionary history. So, on our own planet, we found porphyrins billions of years old. This is really important in regarding the search for life as something that originated really early in evolutionary history on Earth. It might not just exist here, but it could also exist on a neighboring planet like Mars. The generation of life on Mars, because it's so close, is likely to be the same as the generation process of life on Earth. So finding compounds that existed a long time ago without change are key to finding them maybe on another surface. So in this talk, I'm going to be talking about results from experiments using nickel tetraphenyl porphyrin. Henceforth, we're just going to call it nickel porphyrin as a representation of cofactor 430, which is a important enzyme in methanogenic bacteria, as well as chlorophyll B to both represent bacterial chlorophyll and plant chlorophyll. So just the most important part to note between these two structures is that one of them is magnesium centered and one of them is nickel centered. So the central metal of a porphyrin is important because it can affect the properties of that porphyrin. So it can shift its electronic energy levels, which will shift how it changes the UV spectrum. It can alter redox behavior, which you know might be important in regard to the oxidizing reactions we're exploring. Catalytic efficiency, and different types of molecular organization. So it's really important to note the central metal. So those are the two compounds that we're particularly interested in. So we run our biomarker experiments the exact same way I described earlier. We actually run them simultaneously. So when we generate the gas, we're taking that regolith mixture to analyze the ice. We're measuring with a sensor, and then we're also taking the sample from this bottom dish here to analyze. So again, using that layered glass filter paper approach, that regolith sits on top, and then the biomarker sits in this glass dish below. So here we are again including the several different surface simulants that I mentioned. And as our oxychlorine analysis shows that we're likely generating more than one gas, it's possible that these different gases will affect the biomarkers differently. And we do see different fragments from the same structure across our experiments here. So the chlorine dioxide, as I said, generates really quickly. We run our experiments in 20 minutes or less, and the gas actually generates in under 10 minutes. And due to its density, hold on one second. Sorry. Due to the gas's density against the surrounding CO2 atmosphere, it will sink downward towards the biomarker simulant. So it's sinking through that glass filter paper through the simulant to interact with the biomarker. And then after the experiments run and we disconnect everything, we then take that biomarker sample to analyze. So just to note, several biomarkers, including some porphyrins, are sensitive to UV damage as well. So to isolate the effects of the gas on biomarkers, we did check the UV index beneath that glass filter paper, which we can see here in this figure is comparable to a completely dark chamber. So this ensures that the regolith can be irradiated, but the biomarker is not. So after our experiments, we move into analysis. Much of our biomarker analysis is also chromatographic. We can take our sample down two paths, which you can see here. One is using liquid chromatography, that is the blue line. And then the other is using gas chromatography, which is the orange line. Both of these processes utilize a stationary phase, followed by mass spec detection. With liquid chromatography, we can also acquire UV data, which you can see here. And then we can also perform separation to then take the sample for additional analysis. So we can separate using HPLC and then take that sample separation and run it on GC to get more insight into what the structure is that we're looking at. So we compare our mass spec results to those predicted in our molecular assembly index graphs, as well as to similar compounds found in literature. And then we also acquire standards to run to confirm what we have in our samples. So bear with me, I know this figure is terrible. When we're searching for life, we are thinking about molecules made biotically and abiotically. So meaning how sure are we that the molecule we're looking at is from a life process versus just a chemical process? Insert molecular assembly theory. So molecular assembly theory is a framework made to characterize the information required to build objects or build molecules. So a highly complex molecule can, in principle, be formed by both random and non-random processes. However, the probability of finding multiple copies of a complex object under random process goes down really fast as the number of copies goes up. So the abundance of that object is also considered a signature of selection. So the molecular assembly indices for chlorophyll B and nickel porphyrin are 40 and 25 or 26 respectively. So we can see here on screen. And I know these figures are rough because they look really busy, but that's exactly the only thing I want you to get from them. They have a lot of pathways. So typically a molecular assembly indice number greater than 15 it can be indicative of a biosignature, as that level of complexity typically requires some sort of selection, memory, cell memory, biological processes in order to be created rather than just random chemistry up to chance. So 26 and 40 are considerably biotic according to this theory. And then this computation is useful not just to show that the structures I'm interested in are likely biotic, but also to show potential fragmentation pathways through reversing the formation that we see here. So we can look for these structures in our irradiated or our gas exposed samples to help guide us through our data sets. Where will this go? There we go. Several fragments in UV radiated environments have been published for chlorophyll A just last year. And then we utilize those predictions for how chlorophyll B would fragment in an oxidizing environment. So the structures are nearly identical and the labile bonds are still labile. So the compounds that I have boxed in over here on the left-hand side are compounds that we have detected in our samples as well. So all of these have been detected in UV radiated experiments. And then we've also found them within the gas exposure experiments. So pheophytin, which is the loss of the metal, pheophorbyde, which is the loss of phytol, which is this chain you see at the bottom here, and then phytol. So the first compound that we chose to look for in our chlorophyll B sample was phytol. As in past literature, it was the most easily resolved piece that broke off when irradiated. So to do this, we use derivatization. We derivatize our sample and then run it on the GCMS. We use MSTFA, which is a derivatization compound. Derivatization is really just to make it so you can see your compound easier with GCMS or at all, right? So this replaces active hydrogens in polar structures with a trimethylsilyl group, and that makes the compound more volatile so it can pass through that GC column with a gas mobile phase and then go to the detector. And so using GCMS, we're able to confirm the presence of phytol in our samples, which is really cool. So you can see here again the phytol structure in the bottom left. So the exposure of the chlorophyll B to chlorine dioxide is breaking off this phytol chain from the core porphyrin structure. And we've also confirmed octadecanol in these samples as well, which, given its name, is likely just a additional degradation product of phytol itself. So while we're doing these experiments, we're degrading this core structure, and then whatever that breaks into, it's also being exposed to the gas. So trying to catch that compound before it breaks down further is a bit of a time crunch on our end. So alongside the gas generation, we're also running the UV experiments to compare our chlorophyll B data with the published chlorophyll A data. And what we are seeing on our end is that in a 73-hour irradiation of chlorophyll B, we're not seeing the phytol break off. So we're going to try increasing that time to see if we can really get it knocked off in a UV irradiated environment. So we're also using UV vis to monitor our porphyrins, and I do believe I only have, I think, 6 minutes left here, so I'm going to try and speed run this without sounding insane. So porphyrin compounds have two distinct band areas on a UV spectrum. So you can see them here with the absorbance spectrums for protoporphyrin 9 and hematin. So it's a free base porphyrin and then a metalloporphyrin. So we can monitor changes to the conjugation, substituents, and central substituents using this method. So the relative intensity of the Q bands, which are the four you see here, or the two above, the relative intensity of those are due to where they're positioned of the substituents on the macrocycle ring, which is the porphyrin ring, including the inner nitrogen. So essentially, looking at UV vis data is going to tell us how the porphyrin ring is changing. And we see that here with the chlorophyll B sample as well, where we're seeing some shifts in our absorbance values that indicate the loss of that central metal. Okay. So we also use LCMS to further understand changes to our porphyrin ring. We're unable to run porphyrin itself through the GCMS. That requires what's called a PI-GC, which a pyrolysis GC. It can get to really high temperatures, which are required for the boiling point of porphyrin. Our regular GC can't do that. So we have to use LCMS, which is just a liquid chromatography form, which allows us to look at compounds that are difficult to volatilize. So here we're detecting mass to charge ratios that you can see, the 594 and 536. And what we're doing is we're using those masses and software like ChemDraw to propose possible structures and pathways with chemically feasible ring changes in this environment. So the compound you see on the left, that appears in samples across chlorite and chlorate mixtures, but the compound on the right is only appearing in chlorite mixtures. So again, we're seeing this difference across the simulant mixtures. So if we think back to this data that you saw previously, where we see the formation of different species within the ice water, then we can entertain the idea that there are different gases forming, and those, or at least varying levels of gases forming across samples. And those are responsible for how we're seeing different structures of our porphyrin in each of these environments. And we see this supported in different fragments we've identified across our samples thus far. Which we can see on screen here. Some of the things that we see in the chlorite mixture are not found in chloride or chlorate, or sometimes even the perchlorate sample with the neophytodiene. Additionally, while we haven't done this work with chlorophyll B or nickel yet, we have run experiments using iron-centered porphyrins that show that the increased time spent with the chlorine dioxide gas can change the dominant porphyrin fragment within that sample as well. So this is just a summary of this data where the chlorophyll B structure loses its metal center when exposed to the gas, as well as its vital chain. And then these fragments can go on to fragment themselves in this environment, perhaps forming some shorter chain acids or something like oleomucine, which you see here in the top right. Okay, so nickel porphyrin shows a decrease in concentration, but no obvious absorbance changes when looking at our DAD or the diode array detector that's built into the LCMS. So the concentration is halved. We know something new is forming, but it's not showing up with this detection. So either it doesn't have a strong enough UV absorption, it exists in too low concentration amongst other debris, or the UV window that we've selected doesn't match whatever is absorbing. So we would have to adjust that to be able to see this better. But we are able to detect some fragment compounds using GCMS with nickel porphyrin. So we use the NIST database and some standards for identification. So again, simple summary of these results. Interestingly, compounds found in the nickel porphyrin samples show some retained aromatic structures, as well as some alkanes, which when we're looking at this nickel tetraphenyl porphyrin structure can make sense as those phenols just break off whole. Okay, now that we kind of sped run through that, let's just summarize what we talked about. The chlorine dioxide gas will form in a simulated Martian environment and permeate around and below its point of generation. And it's likely that other chlorine-containing gases are forming on the surface of Mars as well. Complex structures like the chlorophyll B or the nickel porphyrin are still degrading within short exposures to this gas. And this degradation is including oxidized structures not predicted by the molecular assembly queries that we've done. And standards for pre-existing compounds can be used to identify structures formed in a Martian environment. However, these are difficult to obtain. Finding standards for chlorophyll or porphyrin structures is quite difficult. So future work includes selecting and obtaining standards as best we can for preliminarily identified compounds, and then hopefully publication of a summary of this work later this year. So could life survive on Mars? That really depends on how you define survive. Will the core porphyrin structure be found close to the surface on Mars? Given this data, it's unlikely. We're generating this gas. It can permeate around itself. It could be stopped by thick mineral deposits. So potentially farther down beneath the surface of Mars, we could find some preserved porphyrins like we found on Earth. But also survival can be changing into something new, right? So as the porphyrin changes into something like oleomucine or asteric acid, that too can be deemed a form of survival because we're able to use something like molecular assembly theory to trace it back to its starting compound. So with that, I'd like to thank my PI, Sam Cunaves, for his unending patience, my undergrad, Isaac, for his great curiosity and collaboration, and then NASA for supporting this work. And then I'm really excited to answer any questions you guys have in the discussion. I'll stop sharing.
Thank you so much, Bernadette. That was great. All right, if anyone has any questions, we'll jump into our Q&A portion. Feel free to just go ahead. Yes, virtual round of applause. Feel free to go ahead and jump right in. You can stay with your video off or on, or you can also pop them into the chat as well.
Has there been any evidence from any of the rovers, particularly Perseverance, that hints toward survived biomarkers?
So far what we found, thank you for your question. I think your name is Mike. So far what we found is just not quite highly complex organic structures on the surface of Mars, more just like hydrocarbons, something like naphthalene. And right now we're unable to determine if these were of biotic origin. So that's where the molecular assembly theory would come in and really trying to determine what collection of compounds that we've already found could be related back to a perhaps more biotic compound like a porphyrin.
Thank you. Anyone else?
I had a question on the the UV spectrums. So are there specific wavelengths that you're testing? Are you testing across like all UV wavelengths, or like are there any particular ones that are more or less important in your work?
So thank you for your question. So there are some wavelengths that do either photodecompose or excite bonds within oxychlorine species perhaps a little better, but we are not necessarily investigating because we're not necessarily investigating how the UV light itself is changing these environments. We're interested in how the environment as a whole is changing itself and the molecule. We use a UV range. So we use a xenon arc lamp that delivers 190 to 400 nanometers of light. So we're not picking one wavelength. There are labs that do that. That's just not something that we do.
Okay. Is that similar to the like wavelengths that Mars would receive then in
Yes,
that
so
range?
the CO2 dominant atmosphere of Mars filters out a lot of the light below 190. So what we use in our experiments is what would be experienced on the surface.
Okay, cool. Perfect. Thank you.
Thanks.
Thank you. We still have some time for a few more questions. Oh, I see one here in the chat. Brandon, are you able to read what's in the chat?
Yeah, I'll read it.
Okay.
I'll read it. So, I heard you mention something about Enceladus at the beginning. Are you working to use these same techniques for other moons of Saturn slash Jupiter? And do you know what differences there are between the gases slash molecules on Mars and these moons? How likely is life to survive on these environments? So that is a great question. I love talking about Enceladus. It just wasn't in the cards for this talk. So I'm primarily interested in Enceladus. There are a few ocean moons that the astrobiological community is interested in. One of them is Europa, which is a moon of Jupiter. It's a Galilean moon. And then the other one is Enceladus, which is a Saturnian or Cronian moon. And the reason we're interested in those is because they are ice moons, right? So Enceladus, because of its libration data, we know it has a subsurface ocean. So that data basically showed us that the surface was disconnected from the core, and that's really interesting because when we're thinking about the search for life, we want to follow the water, and so the fact that Enceladus has clearly a bunch of water that we know about, that makes it a really prime candidate for investigating life. And so, are there differences between the gases molecules on Mars and those moons? Almost certainly, right? So, Mars is at this point a desert planet, and I put desert in quotes because it has a global water equivalent layer of about 30 meters if you factor in all of its water. Um, but it's covered in salts. There's not a lot of like accessible water for life to use, at least that we know of. It would be brine, it would be ice. There's a lot of CO2 ice. And so there's also the change of the atmosphere, right? So the light is passing, hitting that surface directly that is covered in salts, which, as I've talked about, can generate these gases. Something like Enceladus is different. So there's something called an albedo number, and that's essentially how much a surface reflects. I don't want to spend so much time on this question, I'm sorry, but that's how much a surface reflects. And so Enceladus reflects quite a bit of light off of it. And then it's just thick, icy sheets on its surface. So it's likely not generating something like chlorine dioxide gas, at least that we know about. The reason I'm designing sensors is we're working on missions to send there to learn more about its subsurface ocean to kind of figure out how the compounds differ. But our very preliminary data that we have from the Cassini mission shows that there are some differences between Mars and Enceladus. And then how likely is life to survive on Enceladus versus Mars? I'd say incredibly likely because it has hydrothermal vent activity at the bottom of its ocean. It has an ocean, and those are all really, there's energy, there's nutrients, there's water. I think it has a really high possibility for fostering life. So thank you for your question.
Great. Oh, we have another one. Thanks, Peter, for your question. To what extent are Earth and Mars sister planets in terms of element concentrations? For example, Mars must have much lower oxygen concentrations than Earth. So is there higher chlorate production on Earth?
So there isn't a higher, this is hard. So one of the what is called a reverse biosignature of Mars is the fact that there is so much perchlorate and chlorate present because we have bacteria, we have microbiological activity on Earth that consumes those salts. So this is a hard question to answer because we do generate perchlorate and things like that on Earth, mostly in the atmosphere. But we also have species on our planet and other chemical processes that consume those oxychlorines. So comparing their levels is a little bit difficult. But the reverse biosignature comes into play because Mars has so much. So if life were to develop in that environment, it likely would develop to consume that environment. And so the fact that it's not seemingly being consumed could indicate that there isn't a life process there. But Mars does have way more perchlorate than we do, at least globally. Thanks
Great.
for your question.
Yeah. Okay, any more? We have time for a few more.
Of all of the um, data returned so far from Perseverance, is there any particular data set that, for example, I've heard a lot of discussion about potentially organic mud found at the bottom of craters and so on. Is there any data set that appears to be particularly promising in terms of possible prebiotic detection?
That is a great question again, Mike. There are a lot of there are a lot of data sets on Mars that people can get really excited about in regard to prebiotic life in the shale, in the sediment. There was also the recent findings of like the little sulfide rings, or what they think are the sulfide rings on the surface. Um, it's hard to extend it to prebiotic life because it's so hard to find data on Mars. Like in order to sort of form the conclusion that I think that you're trying to get here, you have to piece together a lot more than just one data set. Like there are a lot of really exciting singular data sets that say like there could be possible life here, or this, striation is indicative of XYZ metabolic process. But it's so hard to prove it when there are so many abiotic explanations for all of this as well. The search for life, that is the largest obstacle, is at this point, there really isn't a completely biotic, 100% certain confirmation of life in a data set we can find. We just have to say this leans toward that. Hope that was at least a little bit toward what you were asking. Someone in the chat has a question though, so I'll talk about that. So what discovery on Mars would most likely change our understanding of life in the universe? Well, actually any. So, if we, so first of all, if we find life on Mars at all, I don't know if it's going to happen in my lifetime. I really hope it does, considering it's what I'm working towards, but it will change our fundamental ideas of like the fact that we are alone in the universe. It is statistically crazy to think about us being the only generation of life. So really any discovery of life on Mars would change our understanding of life in the universe. If we take a little bit of a step down and we want to see what can change our idea of life on Earth, that might be a little bit easier to obtain because of the similarities between our two planets. So much of what we learn about Mars tells us about our own planet, can tell us about global warming, can tell us about how these different things interact with each other as a whole. And I think that we're a lot closer to a discovery that changes how we view Earth than we are the universe, um, just strictly based on it being so similar to our own planet. It's a lot easier to define the chemistry of something and say, aha, than it is to discover life. Great question.
Yes, fantastic. All right, we'll go with one more question or discussion anyone wants to bring to the table before we let everyone go. And I just give my plug any of our future curiosity labs as well.
I had, I guess one more and then one like quick fun one. So I was curious about, maybe you mentioned this, but what was like the temperature range that you were doing your experiments in? Was it like simulating like what part of Mars, like North Poles, like the equator, like was there a particular region you were kind of targeting, or did you just, or if you could talk about that?
Yeah, that's a great question. I'm so glad you asked. I don't really get into the temperature experiments. So we can run experiments. We run them at a couple different temperatures. All of the ones I talked about today were run more as like close to control. So they're run at 20 C. But we can run them down to negative 80 centigrade. And so that is typically negative 50 to negative 80 is what we're looking for in regard to kind of global averages with Mars in regard to observing this like type of chemistry that we see here. So we aren't really shooting for a specific area, just shooting for like a global average. We do the same thing with the pressure. We use a constant pressure, even though it can change seasonally in different areas. So um, the plan is to do all of this same thing that I talked about today at negative 50 and negative 80. Uh, it's not necessarily harder. No, it's harder. It's just making sure that everything stays the same within the experiment. Nothing shatters. The vapor pressure stays the same. Making sure all of that stays consistent.
Okay, that makes sense. Thanks. And I was gonna just say if you could do one experiment like on Mars, like they plop you down and you can like dig a really deep hole and take samples or something. Like if you could do one experiment, what would it be? We can answer that
Oh
after.
yeah,
There's another question as well, but
I'd for
yeah.
sure dig. Um, Theoretically, I'll get to that in a second. Theoretically, can some of these experiments be run in Antarctica? Yes, and they have. There are a couple folks that are running experiments in Antarctica, or with Antarctica samples. I actually will be getting some in the mail, to look for the oxychlorine speciation at different depths in Antarctica, is sort of trying to indicate what might be present in brines on Mars. So yes, that can be done. You have to get approval to go to Antarctica, which I don't have yet. But we can. There are people that have gone and have sent samples back, and I am fortunate to be able to run some of those soon. And then, as to like go back to that other question, if I could do an experiment on Mars, I would never go to Mars. I never want to leave this planet. But if I did, I would certainly dig on that planet as deep as I possibly could and then evaluate the samples at depths because we haven't done that yet. And it would be hard because the ice is rock solid and then the rocks are also rock solid. So have to get a really fancy drill.
If you found oil there, then it'd be self-funding. So,
That's true. I'm not sure I'd tell anyone.
all right, thank you.
Thanks for your question.
Awesome. Well, if there's no more questions, I just want to say thank you, everyone, for joining us today. We're really excited to have you all here. Thank you so much, Bernadette, for this session. This was super exciting and informative. So, yes, thank you all of the virtual round of
Thank
applause.
you guys. I had fun. Thanks for your
Yeah.
questions.
Yeah, I will plug our next Curiosity Lab, which is June 14th. It's at the same time between 3 and 4 p.m. And that one's going to be on planetary defense and potentially hazardous asteroids. So if anyone is interested in that, please go ahead and use the similar registration link for our next one. And we hope to see you all there. This will also be uploaded onto the SSPI network so that you can review this if anything wants to stick with you. So thank you all again for coming, and we hope to see you at the next one. Thank you again, Bernadette.
Thank you for having me.
Thank you.
I just leave, right?
Yes.
Okay. Have a good day.
Thanks. Bye, everyone.